So RC delay. Okay, so basically when I have a resistor and a capacitor here, if I have to calculate the delay, I give an input, step input there, and I take the output here. So now can you tell me the transfer function of this? So what do you get V naught of S by V in of S as?
1 by 1 plus RSC.
Okay, 1 by 1 plus SRC, right? So what is V naught of S? If I give a step input, this will be 1 by S into 1 by 1 plus SRC, right? So now if I solve this using some partial functions, what will I get? V naught of S is equal to what? Can you quickly do it and tell me? Can you quickly do this and tell me what I get? So basically I want you to solve this, sorry, A plus A by S plus B by 1 plus SRC, right? So what do you get? A is equal to what and B is equal to what?
A is equal to 1, B is equal to minus RC.
That's right. So A is equal to 1 and B is equal to minus RC. Are all of you with me? Are all of you able to follow? Oh my God, please answer something. All of you are able to follow this, right? What I'm doing. It's very simple. You would have studied this before. So now with this, can you tell me what is V naught of T? Take the inverse Laplace transform and tell me what is V naught of T. This will be equal to, so 1 by S is 1 power e power minus T by RC, right? Is that right? If I take inverse Laplace transform, this is what I get. V naught of T is equal to 1 minus e power minus T by RC. Now, at this point, let's define a parameter called as propagation delay. Okay, at this point, we define a parameter called as propagation delay. Propagation delay is defined as the maximum time taken for the output to reach 50% of VDD from the time input reaches 50% of VDD. Okay, so basically propagation delay is defined as the maximum time taken for the output to reach 50% of VDD from the time input reaches 50% of VDD. So therefore, in order to calculate T here is nothing but the propagation delay. So I will calculate T. For an input VDD, I can write V out of T is equal to VDD into 1 minus e power minus T by RC. Correct? So for a step input, I get an output V naught of T equal to 1 minus e power minus T by RC. For an input VDD, if I vary VDD from 0, if I give a step from 0 to VDD, then I can say V naught of T is equal to VDD into 1 minus e power minus T by RC. So let's do a sanity check. So when you have T at time T is equal to 0, you have this term equal to 1, right? So therefore V out is equal to 0. What happens when t is equal to infinity? At infinite time, when t is equal to infinity, you will have V naught of t is equal to VDD. Correct? Is this clear so far?
Yes, ma'am.
Okay. So basically now I have to find out what is the t when my output becomes VDD by 2. Okay, what is the time required for the output to become VDD by 2? That will give the propagation delay, right? So when the input is VDD, e power minus TPD, I represent this as propagation delay by RC. Can you solve for TPD now? So what will be TPD equal to?
It is RC times 0.693.
Correct. So what is 0.693? You should take natural log, right? So this will
Yes,
be
ma'am.
ln 2 into RC.
Ma'am, LAN half it was.
Is it half? 0.693.
Yes, ma'am.
Okay, fine. Okay, let me write that as 0.693. Okay. So for now, from now on, we'll ignore this term 0.693. Okay, whatever constant that you get here, and we'll simply equate or say TPD is equal to RC. Okay, so basically 0.693 is the more accurate one. But here from now on, we'll see how do we calculate RC delay. We'll see how to calculate RC delay. So just for the first one to get a feel of it, we did all the calculations. But otherwise, you can see that in order to calculate the delay, you just find out what is the effective capacitance seen through this point, what is the effective resistance seen through this point, and just multiplying the two will give you the RC delay. Right? So from next time, like from now on, that's what we'll follow. So for the first problem, we just derived it, TPD. But from the next time onwards, we'll try to calculate the effective capacitance and resistance from the output node. And then that itself will give us the RC delay. So now, we'll define a few parameters here. Before we calculate the RC delay, so the first circuit for which we are calculating the RC delay is obviously an inverter because that's what we've been studying so far. But before that, we'll define a few parameters. So the first parameter that we are going to discuss here is the unit NMOS. Right? So now, as you all know, the resistance of NMOS when it is acting in linear region varies, right? We have plotted that graph also. So what is resistance given by? When NMOS or when any device is behaving as a switch, resistance is equal to 1 by mu Cox W by L into VOV. We have derived this earlier, right? So basically in the linear region, when VOV varies, the resistance also varies. But when we want to calculate an RC delay, for every VOV, we can't keep calculating R and then C and then calculate the RC delay. Right? So therefore, we make some approximations. So here, we take the effective resistance of unit NMOS is equal to R, where this resistance is nothing but the average resistance of the NMOS when it is behaving like a switch for the least W by L that it can accommodate. I repeat again, here we define a term called as effective resistance for an NMOS when it is behaving like a switch. We know that even when NMOS behaves like a switch with VOV, its resistance varies. But since we do not want to complicate our life by calculating the resistance each time VOV varies, we take the average of all these resistances when the MOSFET is behaving like a switch. And then we define another parameter called the effective resistance, which is nothing but the average resistance of a switch for the least W by L that we can give to that MOSFET. Okay. In other words, I can say this average resistance is inversely proportional to mu n for an NMOS as well as W. Let's keep L constant as well as W. It's inversely proportional. Right? Similarly, we define effective capacitance also for an NMOS. Let effective capacitance for an NMOS be equal to C, which is nothing but the diffusion capacitances, other capacitances that we studied earlier in this course, right? We'll put all these capacitors together and then we'll represent the capacitance as C at gate, drain and source. We know that these capacitances of the MOSFET at gain, drain and source are not equal. But these diffusion capacitances are comparable, right? In order to make the calculations easier, we'll just represent the effective capacitance of a unit NMOS as C at gate, drain as well as at the source. And as you all know, this capacitance is directly proportional to W, right? Epsilon naught, epsilon R, A by D, where A is nothing but width into length, right? So therefore we can write this capacitance is directly proportional to W. So now we'll just try to represent this unit NMOS in terms of capacitors and resistances so that whatever I've told you now will be more clear. Okay. So basically we are representing the resistance and capacitance for an unit NMOS. NMOS with drain, source and gate with minimum W by L. So therefore I say 1. Okay. So from drain to source, you have a resistance R, which is the effective resistance. You have a switch in between. That is, if the switch is closed, it'll give you an effective resistance of R. If the switch is open, it is going to give you an effective resistance of infinite, right? An open switch, basically. So this is drain. This is source. So we represent a capacitance at drain, which is C, which goes to ground because the P substrate is tied to ground. We also represent a capacitance at source, which goes to ground. And we represent a capacitance at the gate, which goes to ground. And I repeat, these values of C, they are not equal, but they are comparable. So therefore, in order to make the calculations easier, we accumulate all the diffusion capacitances at each of these nodes and then just represent all these capacitances with C. Just to make the calculations easier, we are making this assumption. Similarly, here R is nothing but the average resistance of the NMOS switch. Okay, I'll give you some time. Please make a note of this. Do you want me to repeat this unit NMOS again?
Yes, ma'am. Could you please repeat that?
Yes, I'll repeat. So basically, we want to calculate the RC delay, right, of any circuit. So for that, we want all the resistors and the capacitors of the MOSFETs, which are there in the MOSFETs. So therefore, we know that the resistance of the MOSFET when it is behaving like a switch, it is acting in linear region, right? It is in linear region. So we have derived an expression for R in linear region, which is 1 by mu Cox W by L into VOV. And we also know that the resistance of the switch varies when it is in linear region. But we do not want to complicate our life and say complicate the calculations, and we do not want to calculate the resistance at each VOV and then calculate the RC delay. We just want to calculate the approximate RC delay. So what we do, we take an average resistance of the NMOS switch and then we represent that as the effective resistance of the NMOS R. And this is called a unit NMOS because this resistance holds good for an NMOS with minimum W by L that's equal to 1. So therefore, I can write R is inversely proportional to 1 by mu n into W. So similarly, we represent the effective capacitance of the MOSFET at gate, drain and source. So at gate you have CGS, right? You have CGD, you have many capacitors at gate. Similarly at drain you have drain to bulk capacitor, at source you have source to bulk capacitor. We have studied many capacitances. So we do not want to represent all these capacitances individually and then calculate the capacitances at every node and then calculate the delay. We don't want to do that. So therefore, at the gate, what are all the capacitances are there? We just put it as one capacitance C. At the source, what all capacitances are there? We put it as one capacitor C. Similarly, at the drain, what all capacitors are there? We put that as one capacitor C. And again, I know that the capacitances at drain, source and gate, they are not equal to each other, right? But they are all in femtofarads or they are all in picofarads, depending upon the technology that you use. So they are almost equal. Therefore, I say, okay, let me represent all these capacitors using a single variable, which is C, not variable, what do I say? Single constant, which is C. So that my calculations of delay is easier. So mind you here, we are only calculating the approximate RC delay, right? If you want to calculate the actual RC delay, then the calculations are vast, which Cadence or LT Spice will do it for us, right? Here we are only calculating the approximate RC delay. So before calculating the delay, I have just represented the unit NMOS with its R and C's at various terminals.
Yes, ma'am, you can continue.
Yeah, thanks. Okay. So now, say I scale W of this NMOS by K. Okay, that is, I make the width of the NMOS equal to K times the unit width. Suppose I make the width of the NMOS equal to K times the unit width. What do you think will happen to these resistors and capacitors? Will it still remain same? I repeat, so far we studied for a unit NMOS which has minimum W, right? So now I make the width of this NMOS some K times W. Okay. What do you think will happen to the resistors and the capacitors? Will it be same or will it change? If it changes, how do you think it will change?
Resistance will decrease, ma'am. It's inverse proportional to K.
Correct.
W.
So resistance will decrease. Correct. Thank you. So therefore, the resistance will get scaled down by K. Right? The resistance will get scaled down by K and all the capacitors get scaled up by K. So this will be K times C, or I'll write C times K. Okay. So all the capacitors gets scaled up by K. So if I scale the width of a unit NMOS by K, scale up the width of the unit NMOS by K, then the resistance of the switch goes down by K while the capacitors increase by K. So is it fine so far?
Yes, ma'am.
Okay. So now we'll study unit PMOS. Now we'll study unit PMOS. Unit PMOS is again for the minimum W by L. We are studying PMOS again for a minimum W by L. Okay. So do you think the mobility of NMOS and PMOS are equal? Do you think mu n is
No,
equal to
ma'am.
mu p? Yes, mu n is not equal to mu p, right? So generally, mu p will be half mu n. So see, this mobility again, we have studied mobility degradation and all that. It depends on many factors, right? It depends on VGS, it depends on thickness of the oxide, many factors. So therefore, mu p will never be equal to mu n based on the other external factors. Mu p might be equal to half mu n. Sometimes mu p is equal to 1/3 mu n, right? Sometimes even 1/4. So, right? So now, for a unit PMOS, if I have to find out effective resistance and represent it in terms of R itself, then can I represent it as just R? Since mu P is equal to half mu n, now let's consider mu P is equal to half mu n and then go ahead. It can be 1/3, 1/4, we know it. But for the purpose of calculations and understanding further, let's say mu P is equal to mu n, half mu n. So what do you think will be the effective resistance of PMOS now?
2R, ma'am.
2R, correct. Right, now the effective resistance of PMOS will be 2R. What will be the effective capacitance? Will it change? See, capacitance depends on width. Width we have taken minimum only, right? So therefore, will the capacitance of PMOS change?
No, ma'am.
No, it will still be C. So the effective capacitance will still be C. So now can you represent the unit PMOS in terms of capacitors and resistors? Just like we did here. Just like we did here for unit NMOS. Now can you represent PMOS, resistors and capacitors in terms of, you represent that in terms of resistance and capacitors, the PMOS, unit PMOS. So I'll also do it, you also do it simultaneously. So we have source. So this will have a resistance to R. Then it will have a switch. Right? So then there's drain. Okay, this is source. At source, you will have C. See, for a PMOS, this will go to VDD. It won't go to ground. Right? For an NMOS, this capacitance is with respect to ground, but for a PMOS, it is with respect to VDD. Why? Because PMOS is within N substrate or N well basically, and N well is always tied to VDD in the layout. So therefore, these capacitors, the other end of the capacitors will go to VDD, not ground like NMOS. So this is the RC model for a unit PMOS. Is this clear?
Yes, ma'am.
So now what do you think? If mu p is equal to 1/3 mu n, then what will happen to the resistance?
Thrice.
Thrice, 3R. Will capacitance change?
Will remain same.
No, it doesn't change. Because capacitance is only proportional to the width, not the mobility. Right? So now this is clear. Unit NMOS and unit PMOS. Are these two clear?
Yes,
Clear,
ma'am.
right? Yes, clear. Okay, thank you. Now, next. Next we'll study unit inverter. Next we'll study unit inverter. So unit inverter is basically made up of what? One inverter is basically made up of NMOS and PMOS. So if we build an inverter using unit PMOS and unit NMOS, do you think the charging and the discharging times will be same? If we build an inverter using unit PMOS and unit NMOS, do you think the charging and the discharging time will be same? No,
No, ma'am.
right? No. So now if I have to make the effective resistance of PMOS equal to the effective resistance of NMOS, then what should I do to the width of PMOS? How should I size the PMOS so that
Two
I
times
have
more.
an, correct. So I have an effective resistance of both NMOS and PMOS same, right? So if I size the MOSFET, that is PMOS, equal to twice that of, this is Vn, right? So if I size the MOSFET PMOS twice that of the NMOS, then the effective resistance of both PMOS and NMOS are the same, right? And then the charging and the discharging currents will also be the same. So we are doing this sizing in order to get the effective resistance of NMOS and PMOS equal. So one thing you have to keep in mind, any complex circuits that we design, complex when I say maybe universal gates or any circuits for AB plus C or any circuit that we design, you always have to make sure that the effective resistance of the PMOS, this is a PMOS, the effective resistance of the PMOS is equal to the effective resistance of the NMOS in order to get an optimum delay. This is how we have to size the transistors. Okay. So now, since you have made the width of this W, what do you think will be the capacitances of PMOS? Will it still be C?
It will change
It will change to what?
as the same proportion of
Correct.
W.
Yes. So it will change as the same proportion. So now what will be the capacitances? Instead of C, you will have 2C, 2C and 2C at the gate, drain and source of the PMOS. Right? Now can you draw the RC model of an inverter? We know the RC model of a PMOS. We know the RC model of an NMOS, unit NMOS. So then now can you draw the RC model of this unit inverter? I'll give you some time. Please try. Okay, I'll also do it here. Meanwhile, I want you also do it along with me and then check your model along with my RC model. Correct. So I have omitted the gate capacitances because we are only looking at the output charging and the discharging of the capacitors. Right. So basically we want what time does this at this point, we want the delay for charging of the capacitor when it has to switch from 0 to 1 and discharging of the capacitors when it has to switch from 1 to 0. Right. Therefore, I have not represented the gate capacitors here, although you should, ideally you should. But since I am only interested on the output side, I have not represented the gate capacitors. Is that clear? Is that clear? Any doubts in this? Yes, yes, yes.
Can we put that switch at the source above?
Yes, that's basically a switch. Yes, yes. That doesn't make any difference. It's an ideal switch basically.
Okay.
Okay. Right. Any other doubts? Shall we continue?
Yes.
Oh, okay. So, sorry, this capacitor here, nobody pointed this out, right? It should come after the switch, right? It should come after the switch. This is the drain, basically. So, okay, I think this was what one of you told, probably. See, this is the source. So, this will be the drain of the PMOS as well as NMOS. And this will again be the source of the NMOS. So, where should you have this capacitor? You should have it here to see. Okay, I'm sorry. This is right. Is it okay? No doubts, right? You should not have this capacitor before R. R plus switch is a switch, NMOS switch. Clear, no? Is it clear? Do you have any doubts in this? Please respond.
No doubts, ma'am.
No doubts, this is clear. All of you know why this should come below the switch. Because R plus switch is an NMOS switch with resistance R. So therefore, this capacitor 2C should be at the drain, right? So no doubts? Okay. So now, in order to find out the RC delay, we have to find out what is the capacitance seen through this point and what is the resistance seen through this point. So during the charging of a capacitor, this switch is on, right? During the charging of a capacitor, this switch is on. So therefore, the effect, and this switch is off during charging. That is when I say charging, when the input is 0, the output should be 1. So when the output should be 1, then the capacitor at the output should be charged. So during the charging of this capacitor C, some capacitor cap, this is off, right? PMOS is on, therefore it charges like this. So therefore, what is the effective resistance seen through this point? What is the effective resistance of the inverter? Resistance only.
Is it R?
Yeah, it has to be R because there's nothing else, right? Only one path is closed. This path is open. So if you see through this point, if you want to calculate the resistance, you see through this point. At one side you have an infinite resistance. On the other side you have a resistor R. Right? Similarly, when the inverter is discharging, that is when the NMOS switch is closed and the PMOS switch is open. On this side, you will have a resistance R. On the other side, you will have an infinite resistance. Therefore, R effective resistance of the inverter is always R because both the switches cannot be closed at the same time. Right? Do you get that? Any doubts?
Understood.
Understood. Okay. Do you think these capacitors here, this, okay, as well as this, will contribute to charging and discharging of the output? Do you think those two capacitors will contribute to charging and discharging at the output? This capacitor here and this capacitor here. See, both these capacitors are connected like from ground to ground and VDD to VDD, right? So do you think they'll contribute to charging and discharging at the output? No, right? So therefore, as far as charging and discharging of the inverter is concerned, we can ignore these two capacitors. Charging and discharging of the inverter, we can ignore these two capacitors, right? Now let's find what is the effective capacitance seen through this point. We found the effective R. Now we'll find what is the effective capacitance seen through this point. So to find the effective capacitance, what do? You would have learnt even this even in analog. Whenever you want to find the effective impedance seen through this point, you ground all the DC voltage sources, you open all the DC current sources, you give some voltage Vx here and find Ix. Vx by Ix will itself give you the impedance. You would have learned this in AICD, AMC and all that. So with the same concept, can you tell me what is the effective capacitance seen from this point?
Is it
So you,
3C?
yes, 3C, because you ground this, you ground any VDD, right? Because VDD doesn't change and it doesn't contribute to charging or discharging of the time of the capacitor. Delay, it doesn't contribute to delay of the capacitor. Therefore, you ground any VDD, you open any current source and then find the impedance seen through this point. So when you ground this, you see that C is coming in parallel with 2C. Therefore, what is C effective of the inverter? 3C. So therefore, now I can write propagation delay of the inverter, standalone inverter, as 3 times CR. So I repeat this again and then I'll give you some time to copy down. Okay. So now we are trying to find the charging and the discharging time of this unit inverter. So in this unit inverter, you have the width of the PMOS is equal to 2 because we have taken mu n not equal to mu p, and mu p is equal to half of mu n. That's why you have the term 2 here, in order to make the effective resistance of both the NMOS and PMOS equal. Since we have increased the width of this PMOS to 2, at source and drain of the PMOS, we'll have a capacitance 2C instead of C. Now, in order to find out the TPD, we want to find the effective R seen at this point. Although we have two resistors, we know that only one of the switch is closed at a time, right? And therefore, the effective resistance seen through this point at any time is just R. During charging, it will be R of PMOS, and during discharging, it will be R of NMOS. And the effective capacitance seen through this point is C in parallel with 2C, which is 3C. Therefore, we can represent the propagation delay of a unit inverter as standalone unit inverter as 3 times C into R. Can one of you please reply? Yes, yes.
Ma'am, why is it not okay to have like different resistances, but it's okay to have different capacitances?
That's the standard basically. So that's the standard everyone is following. So that you will have
Still, we
equal.
won't get the same delays, right?
You will, right? When it is charging, when the capacitor is charging, it will be R times 3C. When the capacitor is discharging also, it will be R times 3C.
Okay, yes, ma'am.
So you can actually, one can size these transistors in any way in order to get equal rise and fall time. But this is the standard type of sizing. So that's why we are studying this. So this is a very basic level, first level of studying how to size transistors, right? So therefore we are studying this. And one of the concept that we are studying here in order to make the delays equal is make the effective resistances equal for a unit inverter. Do you get that? Once you're familiar with all these concepts, you can size the transistors whichever way you want in order to equalize the delays.
Yes.
Okay. So now with this, I want to ask you a question. I have an inverter here, okay? So let me just draw that again. So V in, and then here you have a PMOS. Okay, if I connect the output of this at the input of another inverter, do you think there will be change in the delay? Okay, let me call this itself as V0, okay? And let it be V0 too. So now do you think there will be a change in the output delay at this point when I cascade it with another inverter, or will it still be 3RC? So again, let me make this 2:1, 2:1.
Will it add
Add what?
3RC plus 3RC?
Why is it 3RC plus 3RC?
For it to reach that VO1 point, it will be 3RC. Then again another 3RC to reach VO2.
No. I want only at VO1. So I want you to tell me what's TPD now. TPD at VO1 only. See, here we calculated it for a standalone inverter, right? This is for a standalone inverter. This is both for charging as well as discharging, right? Now I want you to tell me what's TPD if I cascade an inverter to the output of the first inverter. First of all, will it change or not? Will it change? Or will it still
If
be
we
3R?
consider,
Yeah.
If we consider gate capacitance as infinite, then it will not change.
No, you
Otherwise,
of course have to consider gate capacitances as 2C for this, right? And C for that. So the
then it will
input
change.
capacitance, yeah, correct. The input capacitances of the next stage will load the previous stage, obviously. Correct? So now, basically, if you have another inverter cascaded at this point, due to the PMOS, due to this PMOS, you gate capacitance, you will again have a 2C here, and due to the gate capacitance of this NMOS, you will have a C here. Correct? Because the drain of these two are directly connected to the gates of the PMOS and NMOS, right? So therefore, this capacitance here is due to the gate of the second inverter PMOS, and here it is due to the gate of the second inverter NMOS. Now, what is the effective capacitance? Resistance will anyway won't change. It will still be R because either this is on or the NMOS is on. So resistance will still be R, right? Only the capacitance will change because the gate capacitance of the cascaded inverter is getting added up. Correct? So now can you tell me what's TPD here?
6 RC.
Right. So it will be 6 RC. So basically when you cascade, so if you cascade another inverter here, then suppose say at this point I'll cascade another inverter, 2:1 ratio. Then again TPD will increase. This is what we call as fan out, right? Loading. So therefore there is a limit on how many inverters you can cascade here as well. Do you get that? So as and when you cascade 1, 2, 3 inverters at this point, I mean connect them in parallel, connect 1, 2, 3 inverters in parallel, as these go on adding up, this delay also goes on increasing. That's what I'm trying to tell you. Do you get that?
Ma'am, but fan out is
Yes.
related to voltage, right?
Yes,
This is
voltages. The number of fan out is basically the number of inverters you connect at one point. We'll study that in detail a little later also. What is fan out exactly? Okay, so basically as and when you increase the number of circuits starting of the inverter at this point, the delay goes on increasing. For now, if you have understood this, it's okay.
yes.
Is this clear? Okay, so now say I have mu p is equal to 1/3 mu n. Okay, so then I'll have to size the transistors 3:1 and therefore the delay also increases. So that's another thing you should observe here. Is that right? Is that okay? Guys, are you with me? Is that fine? So basically when I increase, when mu p is equal to 1/3 mu n, then I'll have to size the PMOS in such a way that the resistors are equal, effective resistances. Then I'll have to make the width of PMOS 3 times. So then the capacitances increase and therefore the delay also increases. Is that okay?
Yes, ma'am.
Okay. So yeah, another small topic and we'll wind up. Now, all of you draw a NAND gate with me. AB bar. Is that right? Now, here again, we have to size these transistors such that the effective resistance of each of these branches is equal to the effective resistance of a unit inverter. I repeat again. Now, if we have to size these NMOS transistors and PMOS transistors in such a way that the effective resistance of each of these branches is equal to the effective resistance of an unit inverter, then what do you think should be the size of these? So we'll do the first one together. This is an NMOS branch, right? So this is an NMOS branch, okay, which will turn on only when A and B both are 1. This will turn on when both A and B are 1. So when this NMOS branch is on, we want the effective resistance to be equal to the resistance of a unit inverter. Okay, so then how do you think I have to size these two? What should be the size of these two NMOS? Can I keep it at 1 and 1? Can I keep this at 1 and 1?
2 and 2.
Yes, if I keep this at 1 and 1, then this will have a resistance R, this will have a resistance R. So the series resistance is 2R, which does not match with that of a unit inverter, right? So now if I make the width of this 2, then this will have a resistance R by 2, this will have a resistance R by 2, so that when both the transistors are on and conducting, the NMOS branch will have an effective resistance of R, which is equal to that of unit inverter. Is that right? Did you all get this?
Yes, ma'am.
Okay, do you want me to repeat this? So basically this branch should have an effective resistance equal to that of a unit inverter. And I'll have to size these two NMOS transistors in such a way that the effective resistance when both A and B are on should be equal to R. Therefore, I should make each of this equal to R by 2 and R by 2. Therefore, I make the width of these two transistors equal to 2 and 2. That's it. Right? So what about PMOS? What should be the width of PMOS? I should
Half.
make, 1 minute, I should make each of this branch. There are 2 branches in PMOS now, unlike NMOS. Do you see? There are 2 branches in PMOS now, unlike NMOS. So I should make each of this branch effective resistance to be equal to that of a unit inverter. As in, I should make during the worst case charging, the resistance offered by the PMOS should be equal to R. Then what should be the sizes of A and B?
1.
1.
Should it be 1? I said during the worst case charging.
2, ma'am.
Yeah. So when I say worst case charging, one of the PMOS is on. Right? The other one is off. So I want the resistance of the PMOS that is on to have a resistance R. Then I have to make the size of this equal to 2. So always we consider the worst case charging and discharging times. Okay, not the best case. The best case is when both A and B are on. Then this will have a resistance equal to R parallel R, which is R by 2. That's the best case. But during the design of any circuit, we consider the worst case charging and discharging times. since for an NMOS we have only one path, there is no best or worst case. There is only one case, right? But PMOS, here in this case, we have two paths, two branches. So the worst case is when any one of the MOSFET is on, it should have a resistance equal to R. Therefore, I size both these PMOS transistors as 2 and 2. Is this clear? No, this is important because from now on we'll have to size all circuits. So you should know based on what we are going to size the circuit. This is very important. So that's why I'm asking you again and again. Clear, right?
Ma'am, so if it is 2, then the effective resistance of the above one, the
Yes.
PMOS,
Yes.
I still didn't get it, ma'am.
Okay, I'll tell this again. So now the worst case charge, during the worst case charging, we have any one of these two PMOSs on, right?
Yes, ma'am.
Is that right? Okay. So during that case, we want the impedance seen through this to be equal to R.
Okay.
So one of the transistor is off, only one is on. So we want the resistance seen through this point to be equal to R. So then based on that, you size this transistor. Similarly, the other. When B is off and A is on, we want the resistance seen through this point to be equal to R. Then what should be the size of this? That's how we size.
Okay, ma'am.
Okay. So now we'll do it for, can you do it for NOR? Can you do it for NON? I think it will be more clear if you do it for NOR.
Ma'am, only when only one PMOS is on, we will have R parallel with infinity, which will be R only, right?
Correct.
That will happen if both are at 1, right? If we
No,
have
1,
two, then it will
0.
be
1, 0. When only one PMOS is, you're talking about this, right? NAND only.
yes.
When only one PMOS is on, A will be 0 and B will be 1. I mean, only one of them is on. So the effective impedance seen through this point will be R in parallel with infinity, which is R. So therefore, the size of the transistor must be equal to 2 so that the resistance seen through this point is R. This is a PMOS, no? So to have a resistance R, you have to size it to 2 PMOS.
Okay. Yes, ma'am. Yes.
Is that clear now?
Yes, ma'am.
Okay. Okay, we'll just do the circuit and then wind up. Okay, you have to tell me the sizes of these NMOSs and PMOSs. Again, by comparing this to an unit inverter, you have to make sure that the branch resistance of each of these branches. So here you have 3 branches. One is the PMOS branch and you have 2 NMOS branches. Right? So here NMOS you have 2 branches. So again, the worst case discharging time, it should have a resistance R. Can you tell me the sizes?
Ma'am, are the NMOS 1 and 1?
Very good. NMOS is 1 and 1 because when any one of the NMOS is on, it should have a resistance R. So seen through this point, you should have a resistance R when one of it is on. So therefore, it is unit size. That's right. What about PMOS?
That also 1 and 1.
1 and
It's
1?
4 and
Is
4.
it so?
Ma'am. It's 4 and 4, ma'am.
4 and 4. Yes, 4 and 4. This should have a resistance R by 2. This should have a resistance R by 2. So the resistance is R when width is 2. Width is equal to 2. So for this to be R by 2, which should be doubled, no? So therefore, this will be 4 and 4. That's right. Okay, quickly can you tell me what is the sizing for a 3-input NAND gate? 3-input NAND gate for NMOS, what is the sizing?
Three, ma'am.
Correct. All NMOSs will have 3 because during the discharging, each of them will provide a resistance R by 3, R by 3, R by 3, which are in series, and therefore the total resistance is R. What about PMOS for 3-input NAND? Will it change?
It's 2, ma'am.
Or it will
Correct.
be 2 only.
It will be 2 only because we are considering the worst case only when one PMOS is on. What about 3-input NOR gate? What will be the sizing of NMOS? 3-input NOR gate.
N
1
must be
only.
1 and P must be 6, ma'am.
Correct. N must be 1 and P must be 6. That's correct. Why P must be 6? Because each of the PMOSs must provide us with a resistance R by 3. So PMOS provides us with a resistance of R when width is equal to 2, and it will provide us with a resistance of R by 3 when width is equal to 6. Okay. So we'll discuss this again in the next class, the sizing, and then I'll give you some more circuits for sizing so that you become more comfortable with it. That's because this concept is very important and we'll carry this throughout this chapter as well as further chapters also. So I want you to be very clear with this. Okay, so we'll do a few more circuits with respect to the sizing, and then we'll go for another type of delay which is called Elmore delay, calculating another type of delay which is called as the Elmore delay.
Ma'am.
Yes.
So
Is
while
that fine?
considering the PMOS one, I'm taking nu P is equal to nu N by 2. So from there only I'm writing these, right?
Correct, yes. If mu P is equal to mu N by 3, then the PMOS in the NAND gates will have 3 and 3. Okay.
Yeah, ma'am.
The PMOS in the NOR gate, 2-input NOR gate, what do you think it will have? 2-input NOR gate PMOS width. If mu P is equal to mu N by 3, then what will be their sizes?
2 input, ma'am. NOR gate.
2-input NOR gate.
Input.
All this we are doing with respect to unit inverter, and whatever
6.
I taught, yes, 6 and 6, very good. So whatever we did before is by assuming mu N is equal to half mu P. Based on that, we size the unit inverter, and based on the unit inverter, we are sizing the rest of the circuits. If that base itself is mu P is equal to mu N by 3, then all these sizes will also change. So everything that we are doing here is on the basis of unit inverter. We are only trying to make the worst case effective resistance of any circuit equal to the effective resistance of unit inverter. That is the base for all this sizing.
Yes, ma'am. Got it.
Okay, so the class is over. If you have any doubts, you can ask. Those who want to leave can leave. I am not going to teach anything new. But if you want to ask any doubts, you can ask.